Okay, so today we're going to talk about inelastic collisions. We've already talked about collisions when two objects collide with one another, or the opposite, explosions, when two objects are released from one another in opposite directions. And we've discussed elastic collisions, where when two things collide, their kinetic energy is conserved throughout the collision. So today we're going to look at inelastic collisions, and we're going to see how those differ from elastic collisions. So broadly speaking, an inelastic collision is any collision where the internal kinetic energy of the system is not conserved. So it changes from the initial energy state of the system to the final energy state. And realistically, almost every collision that we observe in the real world, with the exception of actual particles, is going to be some amount of inelastic collision. There are certain objects that will better model and be closer to an elastic collision, things like billiards balls as they bump into one another. But most objects in the real world are going to end up losing internal kinetic energy between them as they collide. Right, and the reason for that is there is some amount of work that's done by forces that are internal to that system, the two objects that are colliding, that's going to change form from one type of energy to another type of energy. So some places where we can either gain or lose energy during a collision are things like thermal energy and sound. We're familiar with these being non-conservative forces that will take energy out of our system and lose them to the environment when an action is performed on our system. So that can happen here in terms of momentum as well. We also get physical deformations of the objects that are impacted. So for instance, when you have two cars collide into one another in a head-on collision, they're going to crumple. And that change in their shape is going to absorb some of that momentum and some of the energy from that system. And then it won't be left to be used as translational motion for those objects afterwards. So we also can end up with some stored energy either being released or stored throughout a collision or an explosion. If you imagine things like muscle contractions will release chemical energy stored within the human body as kinetic energy as you push out. We also can think about springs releasing their potential energy and creating kinetic energy between two objects as they push outward. So no matter what happens throughout the collision, we can look at the initial energy states of the system and the final energy states of the system, and if we compare them, we should be able to determine how much energy was either gained or lost during the collision. All right, so let's take a look at an example problem, and we will keep in mind our conservation momentum equation, and we're going to take a look at this problem. Two toy cars collide inelastically. Car 1 carries a spring which is initially compressed, which means it has some amount of stored potential energy within that spring. And during the collision between car 1 and car 2, the spring releases this potential energy and exerts a force on car 2. The mass of car 1 and the spring is 0.350 kilograms, and the car spring system has an initial velocity of 2.00 meters per second. Car 2 has a mass of 0.5 kilograms and an initial velocity of negative 0.5 meters per second, which means that it's going in the opposite direction towards car 1. After the collision, car 1 is observed to recoil with a velocity of negative 4 meters per second. So it means it starts going backwards. I can label that V1 prime for the final velocity of object 1. So it starts going backwards at 4 meters per second. So first of all, we want to find the final velocity of car 2. So that'll be V2 prime. And we can use this equation to figure that out, our conservation of momentum equation. So if we take m1 v1 plus m2 v2, that should equal mass of object 1 times its final velocity plus the mass of object 2 times the final velocity of object 2. So the sum of our velocities in the beginning should equal the sum of our velocities at the end. Right. And then we can start plugging away to figure out what our final velocity should be. So if I move this guy over to the other side of the equation, m2 v2 prime, and subtract out that m1 v1 prime, we end up with m1 v1 plus m2 v2 minus m1 v1 prime. And then if we solve for v2 prime, they'll end up with m1. I'm just gonna combine these two terms ahead, m1 and then m1 v1 minus v1 prime plus m2 v2, and that would all be divided by m2. So that can get us our final velocity for object 2. If we start plugging in numbers here, we've got 0.35 kilograms times our initial velocity, 2 meters per second, minus our final velocity for object 1, which is 4 meters per second is the speed, but it's negative 4 meters per second going in the opposite direction. And then we can add our momentum, our initial momentum for object 2. So we got 0.5 kilograms is our mass for object 2 times the initial velocity of negative 0.5 meters per second. And then we could divide that by m2, which is 0.5 kilograms. And so v2 prime will be going 3.7 meters per second. And that was positive, so it is going back in the opposite direction from which it came because it started in a negative direction. So that's our final velocity for object 2, for car 2. And then we want to think about, well, what happened with our kinetic energy? So our change in kinetic energy is what we want to find for part 2 of our problem. And our change in kinetic energy is our final kinetic energy minus our initial kinetic energy. And so if we think about our final kinetic energy, we can take the kinetic energy of car 1 at the end, plus our kinetic energy of car 2 at the end, and that is our total kinetic energy of our system at the end, right? And we subtract out our kinetic energy in the beginning of car 1 with the kinetic energy of car 2 in the beginning. And then we can break down this equation to find our change in kinetic energy. We can break down each of our kinetic energy terms into 1/2 times the mass of that object, which in this case is mass of object 1, times the final velocity for object 1 squared, plus 1/2 times the mass of object 2 times its final velocity squared, and we'll subtract out the kinetic energies of both ones from the beginning, right? So the mass of object 1 times its initial velocity squared times 1/2, and then the mass of object 2 times its initial velocity squared times 1/2. And then we just want to plug in numbers for all this. So our change in kinetic energy will be 1/2 times 0.35 kilograms times our final energy for car 1, which is final velocity for car 1, which is negative 4 meters per second. But that's going to get squared, so the negative doesn't actually matter there. Remember, kinetic energy can't be negative. And then we're going to add that to the final kinetic energy for car 2, which is 1/2 times its mass, which is 0.5 kilograms, times its final velocity that we found was 3.7 meters per second. And we're going to square that. And we'll subtract out from that the sum of the kinetic energies in the beginning, which will take, again, that the mass of object 1 times its initial velocity was 2 meters per second squared, and then we'll add the kinetic energy of object 2, which was 1/2 times its mass, 1.5 kilograms, times its initial velocity, which is negative 0.5 meters per second. We're going to square that, so again, the negative doesn't really matter. And so if we plug all that into our calculator, then we end up getting a change in energy of 5.46 joules. So what we did, right, was we took the sum of our final kinetic energies and subtracted out the sum of our initial kinetic energies, right? And that difference is how much work the spring did on our system, which in this case was 5.46 joules worth of work. All right, so we ended up with some change in kinetic energy for our two cars, and the reason for that, right, is that the spring, the potential energy of the spring, ended up releasing kinetic energy into our system when those two cars collided. So an inelastic collision, again, is going to cause a change in the total kinetic energy from the initial to the final states of our system. If we have something that is quote unquote perfectly inelastic, then what happens is the two objects that are colliding with one another stick together after the impact. This could be something like a skater jumping onto her skateboard from running start. So she's going to have some momentum in the beginning. The skateboard's going to be sitting there. When she jumps onto it, they're going to keep moving together as one object, as one mass. A football player catching a passed ball. So the ball's going to have some momentum. The football player, as he runs, may have some momentum. When he catches it, they are now moving together as one mass together. A hawk catching another bird midair. Again, they have two separate momentums before they collide, and then afterwards they continue moving together as one mass. So these are examples of perfectly inelastic collisions. And the reason why they're perfectly inelastic is because since they stick together after the collision, we're going to maximize the amount of kinetic energy that we can lose from this collision. And because the masses will become one after the collision, then we can slightly modify our conservation of momentum equation to say the momentum of object 1 before the collision, the momentum plus the momentum of object 2 before the collision. Once they collide, they now start moving together as one thing. So if we just add their masses together, they're going to have the same velocity because they're moving together. So in the second half of our equation for final momentum, we can just say that the sum of their masses times their final velocity because they have the same final velocity at the end. So m1v1 plus m2v2 equals, in parentheses, m1 plus m2, or the sum of their masses times the final velocity they're going to have as they move together after the collision. And so let's take a look at an example. So in this problem, we're going to have an ice hockey goalie who's at rest when he catches a hockey puck coming at him for a shot. And if the puck is moving at a velocity of 35 meters per second while he's at rest, then we can find how quickly they're moving afterwards once the hockey puck collides with the goalie. And we can determine how much kinetic energy was lost during this collision. Okay, so now let's take a look at the ice hockey goalie catching the hockey puck. So again, we can start with our conservation of momentum equation. So we got m1 times velocity of object 1. In this case, we'll think of object 1 as our hockey goalie. And if we add that momentum of object 1 to the momentum of object 2 in the beginning, that should equal the momentum of object 1 times its final velocity, the mass of object 1 times its final velocity at the end, plus the mass of object 2 times its final velocity at the end. The difference here, though, right, is that when the hockey goalie catches the hockey puck, they become one thing moving together, right? So since our v1 prime, or the final velocity of our goalie, equals v2 prime, or the final velocity of our puck, we can just say those two things are the same thing, and let's just call them v prime. So I'm going to get rid of v1 and v2 from our final velocities, and we can rewrite that as m1 plus m2. We can factor out our final velocity for that hockey goalie, hockey puck system. And that's still going to be equal to m1 v1 plus m2 v2. That equals the sum of our masses, so the combined mass of our hockey player plus the hockey puck times the final velocity of the two of them moving together. Great. So then if we think about what variables we know that our hockey goalie is 70 kilograms, and we know that our hockey puck weighs 0.150 kilograms. Our goalie was at rest, so his initial velocity is 0 meters per second, and the hockey puck was traveling initially at a speed of 35 meters per second in the direction of the goalie. So since we have a velocity of 0 for the hockey puck, or sorry, for our goalie initially, we can get rid of the goalie's initial momentum, right? And then we're left with just the mass of our hockey puck times the initial velocity of our hockey puck equals the combined mass of the hockey puck and the goalie times the final velocity, right? And if we wanted to solve for the velocity by itself, we could just divide by that combined mass of the hockey puck and the hockey goalie, and whatever you do on one side, we're going to do on the other side. So we end up with our final velocity is the momentum of our hockey puck, the initial momentum, divided by the sum of the masses of the goalie plus the hockey puck itself, right? So if we fill in our known variables here, we've got 0.15 kilograms for the hockey puck that was moving 35 meters per second, and then divided by 70 kilograms plus 0.15 kilograms. And if we do out the math there, we end up with a final velocity of 0.0748 meters per second is how quickly the goalie and the hockey puck will be moving backwards from the goalie's perspective after the goalie catches the hockey puck. And it makes sense that they're moving so slow because obviously the hockey puck has all of our initial momentum, right? And it's moving very fast, 35 meters per second, but it's very slow relative to the goalie. And so when the hockey puck and the goalie combine together as one object, they have a significantly larger mass than the hockey puck by itself. So they'll be moving much smaller because of the conservation of momentum. And then finally, we can figure out how much kinetic energy is lost during this collision. Change in kinetic energy. And our change in kinetic energy will be whatever our initial kinetic energy is, subtracted from our final kinetic energy. And of course, we can separate that out into the final kinetic energy of object 1 plus the final kinetic energy of object 2 minus the initial kinetic energy of object 1 combined with the initial kinetic energy of object 2. And if we look at our initial kinetic energy, again, since our goalie was not moving initially, then there was no initial kinetic energy for him. So we just need to subtract out the initial kinetic energy of our hockey puck. And so we can break that equation down into 1/2 times the mass of our goalie times his final velocity squared plus 1/2 times the mass of the hockey puck times its final velocity squared minus 1/2 times the mass of the hockey puck times its initial velocity squared. And of course, if we wanted to, we can further combine our objects after they've collided, and 1 plus m2, we can combine those terms of the final velocity squared and still subtract out our kinetic energy at the end, or sorry, from the beginning for our hockey puck. And then if we plug in our numbers over there, we end up with 70 kilograms plus 0.15 kilograms times our final velocity, which we found to be 0.748 meters per second. We'll square that and subtract out 1/2 times the hockey puck's mass and times its initial velocity squared, which is 35 meters per second squared. So that gives us 0.196 joules for our final kinetic energy and 91.875 joules for our initial kinetic energy coming just from the hockey puck because the goalie's at rest. And then when we subtract those, we get a final change in energy of negative 91.7 joules. And so we lost in this collision 91.7 joules, which again, this is a perfectly inelastic collision. So we're gonna lose the maximum amount of kinetic energy that we can through a collision when we have those two objects colliding and becoming one object moving together after a totally inelastic collision like this.